In this video, we look at summing an infinite series. All right, so what is an infinite series? A sum of the form n equals 1 to infinity, a sub n is an infinite series. Right, but how do we make sense of this, right? We're summing up an infinite number of terms. Well, what we do is we look at partial sums. We define the nth partial sum as S sub n equals the sum n equals 1 to capital N of a sub n. Right, so essentially the nth partial sum is the sum of the first big N terms. Okay. Then we look at the sequence. Of partial sums. Right, S1, S2, S3, so on and so forth. And we look to see if the sequence converges. Right, so we say an infinite series converges if the limit as capital N goes to infinity of S sub n equals S, right? In English, if the sequence of its partial sums converges to some value S. In such a case, we write that S is equal to the infinite series. If the limit capital N goes to infinity of S capital N does not exist, the infinite series diverges. So let's look at the series sum n equals 1 to infinity of n over n plus 1. All right, we're going to determine if this converges. Well, let's start off by just calculating partial sums. So the first partial sum would be 1/2. Then we get a half plus 2/3. Then we get a half plus 2/3 plus 3/4. Then we'll get a half plus 2/3 plus 3/4 plus 4/5. All right, so on and so forth. However, notice that the second partial sum will be greater than a half plus a half. Right, because 2/3 is larger than a half. Notice that the third one will be greater than a half plus a half plus a half. All right, so 3 times a half. The fourth one is larger than a half plus plus a half plus a half, or 4 times 1/2. So what we can say is, in general, the kth partial sum would be larger than k times 1/2. Right? Notice that what this means is that the sequence S sub n is unbounded. Which implies that the sequence of partial sums diverges, which implies that the series n equals 1 to infinity of n over n plus 1 also diverges. Next, let's look at the sum n equals 1 to infinity of negative 1 to the n. And again, we want to proceed in much the same way. And so S1 would be negative 1. S2 would be positive 1. I'm sorry. S2 would be negative 1 plus 1. S3 would be 0 minus 1. S4 would be negative 1 plus 1. All right, so on and so forth. So our sequence is negative 1, 0, negative 1, 0, so on and so forth. And this clearly diverges. So therefore, this series diverges. Now let's consider the sum n equals 1 to infinity of 1 over n times n plus 1. S1 is equal to a half. S2 is a half plus a sixth, which is 2/3. S3, we get 2/3 plus an eighth. Not an eighth, I'm sorry, and a 12th. Right, that is 3/4. S4 is 3/4 plus a 20th. That is 4/5. Right, well, notice what's happening. We tend to have a pattern. So let's say S sub n appears to be n, right, over n plus 1. That's what it appears to be. Now, we need to prove this. So first, take a look at 1 over n times n plus 1. It is fairly straightforward to show that this is 1 over n minus 1 over n plus 1. So S sub n would therefore be equal to 1 minus a half plus a half minus a third plus a third minus a fourth plus so on and so forth up until we got to 1 over n minus 1 minus, 1 over n minus 1 over n plus 1. Well, notice the halves cancel out, the 1/3, the 1/4, and the 1 over n. We're left with 1 over n plus 1, which is indeed n over n plus 1. By the way, such a series is called telescoping. Right? Because notice, all of your middle terms cancel out. So that all we're left with are the two end terms. So now we have Sn. Well, take a look. The limit as n approaches infinity of Sn is the limit as n approaches infinity, n over n plus 1, which equals 1. So this series converges, and we say the series, this infinite sum, equals 1. Well, let's consider two series. All right, so consider the infinite series a sub n. Let's say that converges to some value L. And another series, b sub n, let's say that converges to some value m. Let capital A sub capital N represent the partial sums for this first series, and capital B sub capital N represent the partial sums for this series. Notice then that what we have is this limit would equal L, and this limit would equal M, right? Well, now let's consider the series C a sub n plus or minus b sub n. If we look at this nth partial sum, right, CA1 plus or minus B1 plus CA2 plus or minus B2 plus so on and so forth plus C a sub n plus or minus b sub n. Well, we can split this into two. So we have CA1 plus CA2 plus so on and so forth plus CAN, then plus or minus B1 plus B2 plus so on and so forth plus Bn. That first grouping, we can factor out a C. That second grouping, isn't that the nth partial sum for B? So that'd be B sub n. But now that first grouping is this, isn't it? It's the partial sum for A sub n, right? So we have S sub n is equal to this. So now if we take the limit of S sub n, this is the limit of CAN plus or minus BN. And using properties of limits, this becomes C times the limit of AN plus or minus the limit of BN. But that first limit is L, right? And that second limit is M. Notice what this means then is that this series converges to C times L plus or minus M. This is known as the linearity property, right? Because then we can conclude this. So in other words, the infinite series are linear. So if A sub n and B sub n converge, then this series and this series converge for any constant C. And we have this and also this. Right, so in other words, a series splits across addition, subtraction, and you can factor constants out of series. Right, this is what it means for something to be linear. A special type of series is the geometric series. And so a geometric series with common ratio R, which is not 0, is a series of the form sum n equals 1 to infinity C R to the n, where C is also non-zero. Right now, if we look at the nth partial sum, right, we're going to get C plus CR plus CR squared plus so on and so forth plus CR to the n. Now, this means that if we multiply both sides by R, we get CR plus CR squared plus CR cubed plus so on and so forth plus CR to the n plus 1. Now, take the difference. Notice what we're left with. C minus CR to the n plus 1. Factor out an S sub n. And factor out a C. And we get our partial sum, S sub n, as C times 1 minus R to the n plus 1, all over 1 minus R, as long as R is not equal to 1. Now let's take this limit. All right, so we have the limit of c times 1 minus r to the n plus 1 all over 1 minus r, which equals c over 1 minus r times that limit of 1 minus r to the n plus 1. Well, this is clearly c over 1 minus r minus c over 1 minus r times this limit. Now, if the absolute value of r is less than 1, then notice that this limit is 0, which would imply that our overall limit of the sequence of partial sums would be c over 1 minus r. If the absolute value of r is greater than 1, notice that our limit does not exist. Which means that our sequence of partial sums diverge. Now, if r happens to be 1, then notice that we have this series. It's just c, right? Now this clearly diverges. If r happens to be negative 1, right, then we get negative 1 to the n times c. So it's going to alternate between plus and minus c. So this also clearly diverges. Right, we've shown that, right, by up here. Where was it? Where was it? There it is, right here. We can now summarize our findings. So let's see, not equal to 0. If the absolute value of r is larger than 1, less than 1, then the geometric series converges to c over 1 minus r. If the absolute value of r is greater than or equal to 1, then the geometric series diverges. So this result is one of many that you may want to write down somewhere because it is that important. Now we're going to see a really interesting application of the geometric series. What we're going to do is we're going to take 3.26 repeating and write it as a fraction. Well, write this. 3 plus 26 over 100, right? Then what's next? 26 over 10,000. Then what's next? 26 over, what, 1,000,000? Right, so on and so forth. Well, this becomes 3 plus 26 over 10 squared plus 26 over 10 to the 4th plus 26 over 10 to the 6th, so on and so forth. We can factor out 26 over 10 squared. Be left with 1 plus 1 plus 1 over 10 squared plus 1 over 10 cubed plus so on and so forth. Well, this can be rewritten as 1 over 10 squared to the 0th power plus 1 over 10 squared to the 1st power plus I'm sorry, this is not a 10 cubed, right? This is a 10 to the 4th. Right, then plus 1 over 10 squared to the 2nd power plus so on and so forth. Well, notice that is this, which is geometric. So I may need to change a couple things, right? That should be n equals 0. Right, so geometric sequence is defined to be the sum n equals 0 to infinity, not n equals 1 to infinity. That is my fault, so let's correct those right now. Well, that's a geometric sequence with ratio 1/10, right? So we know that converges. It converges to 1 over 1 minus 1 over 10 squared. So I'm going to rewrite that. Now it's 26 over 100. Then we get times 1 over 99 over 100. That is 3 plus 26 over 99. So now 3 times 99 plus 26, we get 323 over 99. Right, so 3.26 repeating is 323 over 99. So now let's take a look. If we take a look at the nth partial sum, that is a1 plus a2 plus a3 plus so on and so forth plus a sub n minus 1 plus a sub n. Right, there's a reason I wrote it this way, because if we take a look, isn't that the n minus 1 partial sum? right? So we can now write this as the n minus 1 partial sum plus just the nth term. This allows us to write a sub n as the nth partial sum minus the n minus 1 partial sum. Let's assume that this infinite series converges to S. Then what do we have? The limit as n goes to infinity would be the limit as n goes to infinity of Sn minus Sn minus 1, which can be split up but both of those limits are the same thing. They're S. So we get 0. What this implies is that if the limit as n approaches infinity of a sub n is not 0, then the infinite series cannot converge, meaning it has to diverge. This is known as the nth term divergence test. Excuse me, my technology is acting up. So this is something else you may want to write down. So write this down with the geometric series convergence. And keep it handy. The nth term divergence test, which basically says if the terms of your sum do not tend to 0, then the series will diverge. What this does not say, however, is that if they tend to 0, then it converges. All right, let's look at this series. What we do is we take the limit of the nth term. You can see that that limit is a third, which is clearly not 0. So divergence test tells us that this series diverges. Let's now look at this series. So again, what we want to do is we want to take the limit. Well, this is going to be e to the limit. Right? Well, that limit is 0. Right? So this is e to the 0, which equals 1, which clearly is not 0. Therefore, our series diverges, again, by the divergence test. Let's now look at this series. Well, if we take the limit, we get 0. Okay. This does not mean, right, so it does not imply that our series converges. Right, what it means is that the test itself is inconclusive. So let's take a look at the nth partial sum, where you get 1 plus 1 over root 2 plus 1 over root 3 plus so on and so forth plus 1 over root n. Well, notice that this will be greater than or equal to 1 over root n plus 1 over root n plus 1 over root n plus so on and so forth plus 1 over root n. And there are n of those terms. So this equals n over root n, which just simply equals the square root of n. Now if we take a look at this limit, that is infinity. This means that this series diverges.